Today, we will study a fantastically competent linear classifier. It is called the support vector machine. So we'll begin by talking about the margin of a linear classifier, and then we'll formulate the problem of finding the linear classifier that has the largest margin possible. This will turn out to be a convex optimization problem, which means that it's actually pretty easy to solve. And it'll turn out that the solution has a unique property. It only depends on a few of the training points, which we call support vectors. And this is why the method overall is called a support vector machine. Okay, when we were talking about the perceptron algorithm, we mentioned that there is this convergence theorem, which says that if a data set is linearly separable, then the perceptron algorithm, those 4 lines of code, are guaranteed to find a linear classifier that perfectly separates the training set. So in this picture, for example, it'll return something that could be one of these lines, or maybe this one, or maybe this one, something like that. But what if we want the linear classifier that is the most central? Maybe something like this. The classifier that has the most buffer around it, for example. How would we even formulate that? What does that mean? So let's take a closer look. Okay, so the setting is that we have training data, say n points, x1 through xn. These are some d-dimensional vectors. And we're looking at binary classification, so each point has its label y, which is either +1 or -1. Now we want to find a linear classifier, so we want to find W and B that perfectly classifies this data. Okay, so if y is +1, W.x plus B should be positive. If y is -1, W.x plus B should be negative. And last time we saw that a concise way to write this is to simply say that y times W.x plus B should be greater than 0. Either they're both greater than 0 or they're both less than 0. Okay, and we want this condition to hold for every one of the n training points. Now, in order to start talking about margins, what we're going to do is to take this condition and reformulate it just a tiny bit. We'll write it like this. Instead of asking that y times W.x plus B be greater than 0, we'll ask that it be greater than or equal to 1. Okay, why can we do this? It seems like a stronger condition. Certainly, if y times W.x plus B is greater than or equal to 1, then it's greater than 0. So it certainly implies that. But it seems like it's something more. It seems like it's requiring more. And it's actually not. If you can solve this, if you can find W and B that solve that, you can also find W and B that solve this. And let me explain why. Okay, so let's say you manage to find a W and B such that for all the training points, y times W.x plus B is greater than 0. So let's look at what these values actually are. Maybe for the first training point it's 3.2, something greater than 0. Maybe for the next training point it's 1.6. Maybe for the next one it's 0.1. Maybe for the next one it's 2.3. And all the way to the nth point, maybe it's 1.0. Okay? So we have these n different numbers, and they're all greater than 0. Let's look at the smallest of them. Let's say it's this one, and let's call it epsilon. Now, if we take W and B, and we multiply them by 1 over epsilon, if we just scale them up by a factor of 1 over epsilon, then W.x plus B also gets magnified by 1 over epsilon, in this case by 10. Okay? So the first number will become 32, and the next number will become 16, and the next number will become 1, and the last one will become 10. And in this way, all the numbers become greater than or equal to 1. Okay? So if you can find W and B such that y times W.x plus B is greater than 0, then by simply scaling up W and B, you can get the second condition as well. You can make all of these values be greater than or equal to 1. Okay, so this is the condition we'll be working with. This will be our linear separability condition. Okay, that makes sense, but why did we actually do this? How did this help us to rewrite our condition in this way? Well, it will turn out that if we write our separability condition in this way, it's very easy to come up with a nice formula for the margin. Okay, and let's see what that is. Okay, so now we're going to have some decision boundary, w dot x plus b equals 0, and that's the thick green line in the middle. What is w dot x plus b equals 1? That is a parallel hyperplane, okay, and it's shown by the dotted line over there. And what's w dot x plus b equals minus 1? That's another parallel hyperplane on the other side. So in this condition over here, in our separability condition, what we're insisting is that all the positive points, in this case the blue triangles, have to be to the right of the right hyperplane. And all the negative points, in this case the red circles, have to be to the left of the left hyperplane. Okay, so not only do they have to be on the correct side of the boundary, but also there should not be any points in that middle buffer zone. Okay, and the margin is the width of the buffer zone, for which I'm using the Greek letter gamma. That's the margin, and that's the thing we want to maximize. Now it turns out that there's a simple formula for the margin. The margin is simply 1 over the length of W. Why is that? Well, you can just take my word for it. It's just a simple geometric argument. You don't need to know what it is. In case you're curious, I'll just give you a quick hint. Okay? So let's look at our right hyperplane and look at any point z on it. Okay? So the point lies on the hyperplane, so we know w dot z plus b equals 1. Now we also know that if we move gamma units in this direction, we land on the decision boundary. What is this point over here? What is this point gamma units in that direction? Well, it's z minus gamma in the direction of w. Okay? Actually, w might not be a unit vector, so we have to normalize it to make it a unit vector. And if we do that, then we end up with that point. Now, since that point lies on the decision boundary, we know that w dot that point plus b equals 0. And when we solve these two equations, we get our formula for the margin. Okay? At any rate, we now know what the margin is. It's 1 over the length of w. And since we want to maximize the margin, what we need to do is to simply minimize the length of w. So this is the optimization problem we want to solve. We have our n data points. We want to perfectly classify all of them. That's this condition over here. And while perfectly classifying those points, we also want to maximize the margin. So we want to minimize the length of w, or equivalently, minimize the length of w squared. So this is an optimization problem that we want to solve, in which the things we're solving for are w and b. So how do we solve this problem? Okay. Well, the nice thing is that this turns out to be a convex optimization problem. Now, soon, maybe in a couple of lectures, we'll define exactly what this means. But for the time being, the reason it's a convex optimization problem is because the thing we're minimizing is convex. We know the length of w squared is convex. That's one of the examples we saw. And all the constraints are linear functions of w and b. So when you have a convex thing that you're minimizing and all the constraints are linear, that's a convex optimization problem. And it means that it's pretty easy to solve. You can just hand this over to some standard package and it'll give you back the answer. Okay. Now there's a second benefit of convex optimization, which is not only can you solve the problem efficiently, but you can use the theory of duality to also tell you a little bit about what the answer looks like. Okay, and this also, I'm sure, sounds somewhat mysterious, and it's also something we'll talk a little bit more about later on. But let me tell you what duality theory tells us. it tells us that the solution is of a particular form. The solution looks like this. It is the sum over all data points of the data point times its label, which is +1 or -1, times some coefficient, which is greater than or equal to 0. Okay? So for each data point, there's some coefficient alpha sub I. And the solution, W, the optimal W, is just a linear function of this form. Alpha I times the label +1 -1 times xi. Okay? Now the remarkable thing is that most of these alpha i's may well be 0. Okay? The only alpha i's that are going to be non-zero are for the points, the data points that lie exactly on the margin. In this data set, there's just 4 of them. These are called the support vectors. For all the other points, the coefficients alpha I will be 0. So in this case, in this example, W will be a function just of the 4 support vectors, the 4 data points that I've circled. Okay, so you could have a data set of 1,000,000 points, but if there's just 100 of them that lie on those margins, then the final answer is a function just of those 100 points. Okay, let's see a quick example of the SVM at work. And this is a very famous data set called the IRIS data. Okay, so it consists of measurements of 150 flowers, which are all irises of 3 different types. There's Iris setosa, Iris versicolor, and Iris virginica. There's 50 of each of them, so 150 points total. Okay? And for each flower, 4 measurements were taken: the petal length and width, and the sepal length and width. And the goal is to take these 4 measurements and predict which of the 3 types of iris it comes from. Okay? So here's a plot of the data. Since we're doing binary classification, I just pulled out 2 of the 3 classes. So I pulled out setosa and versicolor. The setosa are shown by red circles. Versicolor are shown by black triangles. These are the 2 classes. And for visualization purposes, although there are 4 features, I just pulled out 2 of them. Okay, so we'll just use 2 of the features, the widths of the sepals and petals. So you can see the data set. Is it linearly separable? It certainly is. So if we were to use the perceptron algorithm, it would indeed find a classifier that was perfect on the training set. Okay? But let's see what the SVM does. This is what it returns. A very nice linear classifier, the one right in the middle. Okay? So this linear classifier depends on just these 3 training points. It's a function of just those 3 support vectors. And the margin is this distance over here, this gamma. And this is the largest margin possible on this data set. Okay? So a very competent linear classifier indeed. Okay, well that's it for today. We've got our first glimpse of the support vector machine. And what we did today was to focus on the case where the data is linearly separable. Now, in practice, this is usually not the case, or at least fairly often not the case. So what we'll do next time is to look at the case of arbitrary data, and it'll turn out that this same methodology extends very easily to that more general setting. So see you next time.